In this problem, a boulder of mass 45 kilograms is pushed on a surface with a coefficient of kinetic friction of 0.85. The fact that it will be sliding against the surface means that we need to look at kinetic friction. We need to figure out what horizontal force must be applied to this boulder to produce an acceleration of 0.2 meters per second squared. So first we need to look at some of the forces that are acting on the boulder. One of the forces that's acting is the weight of the boulder. And to calculate the force of gravity, just like always, we take the mass and we multiply by 9.8. So the mass is 45 times 9.8, which is 441 newtons. Because this is on a horizontal surface and there are no other vertical forces being applied, this means that the normal force is also going to be 441 newtons. If this was on an incline, or if the applied force was acting at an angle, we would need to figure out what the normal force is. Again, the normal force is important when we're going to calculate the force of friction. We have an unknown force F that's pushing this boulder forward, and this force is causing the boulder to have an acceleration of 0.2 meters per second squared. So I'm going to be setting this up so that the acceleration is to the right. I'm going to make the right the positive direction. But there's one force that I haven't included yet, and that's the force of friction. If this is sliding to the right, then the force of kinetic friction is acting to the left on the boulder. And the first thing that we need to do is we need to calculate that force of kinetic friction. The way that we do this, the force of kinetic friction equals the coefficient of kinetic friction times the normal force. So we're given both of those quantities. The force of kinetic friction is going to be equal to 0.85 times 441. So that gives that the force of kinetic friction is 374.85 newtons. Now we're ready to go through and solve the problem. We're going to set this up looking at all the forces. So the net force on this boulder is the sum of all of the forces acting. We have the unknown force F acting to the right, and we have the force of kinetic friction acting to the left. Because it's acting to the left, and I was making the right the positive x direction, then that means the force of kinetic friction is going to be negative. So this is going to be the unknown force F minus 374.85 newtons. We also have that the net force equals the mass of the object, 45 kilograms, times the acceleration of the object, 0.2 meters per second squared. And if we do that, 45 times 0.2 is 9 newtons. And so combining those two things together, we have that F minus 374.85 is going to equal 9, or the unknown force that we're applying to the right is 383.85 newtons. And when doing these problems, there's not much of a difference between these problems and the other force problems that we have been working on. Going through them, the only thing that's different is how we actually calculate the force of friction. Instead of just being told that there's a force acting to the left of 374.85 newtons, we need to actually go through and find that force. In this next problem, we have a wooden crate that's being slid across the floor at a constant velocity. And there's a force of 30 newtons that's pushing on it to the right to keep it moving at a constant velocity. And we're going to calculate the coefficient of kinetic friction between the crate and the ground. So first, we're going to calculate the weight of the object. The weight of the object is going to be 12 kilograms times 9.8 meters per second squared, which is 117.6 newtons. Again, there are no other vertical forces acting, so that means that the normal force has to balance out the weight. So the normal force is also 117.6 newtons. And then we have this force of kinetic friction acting to the left. Now in this, we're told that it's moving at a constant velocity. Again, this is something you have to be careful on. It's not saying that it's moving with a constant acceleration. It's saying that the velocity is constant. And if the velocity is constant, that means that the acceleration is 0. If the acceleration is 0, that means that the net force must be 0. Now again, some people might say, well, how is it moving if the force is 0? Well, Newton's first law says an object in motion will continue in motion at a constant velocity unless there are unbalanced forces. So here, the forces are balanced, so it will continue moving with a constant velocity. There needed to be a net force to make it start sliding, but that's not the situation that we're looking at here. So if it's moving with a constant velocity, this tells us that the force of friction must be 30 newtons. And so then using the equation that the force of kinetic friction equals the coefficient of kinetic friction times the normal force, we're able to go through and solve for the coefficient of friction. We know that the force of friction is 30 newtons. We're looking for the coefficient of kinetic friction, and we know that the normal force is 117.6 newtons. So then dividing 30 by 117.6, we get that the coefficient of kinetic friction is 0.255. Again, the coefficient of kinetic friction is a unitless quantity. It's the ratio of the force of kinetic friction to the normal force. So this is something that describes how rough the surfaces are, and it relates how rough the surfaces are and how hard the surfaces are being pushed together to the force of friction that's acting on the object. Again, this is a very basic problem. It's very common to be looking at these problems where it's moving at a constant velocity to see if you catch that. That means that the net force is 0. But then as you go through this, it turns out to be a very simple problem in solving for the coefficient of friction. In this next problem, we have a box that's being dragged across the ground by applying a force acting at an angle. So this one's going to be a little bit different than the previous two problems. This one, the normal force is not going to equal the weight of the object. So we have this 45 Newton force acting at a 30-degree angle. The first thing that we need to do is we need to break that force into horizontal and vertical components. This x component is going to be 45 times the cosine of 30 degrees, which is 38.97 newtons. The vertical component of the applied force is going to be 45 times the sine of 30 degrees, which is 22.5 newtons. We also have the force of gravity acting on the object. The force of gravity will be 12 times 9.8, which is 117.6 newtons. We also have the force of kinetic friction acting to the left on this object. Now, a common mistake is to say that the force of kinetic friction is going to be the coefficient of kinetic friction 0.3 times 117.6. That is not true. The force of kinetic friction is the coefficient of friction times the normal force. So we're going to need to calculate what the normal force is. To do that, we're going to use the fact that all of the upward forces added together must equal all of the downward forces added together. In the upward direction, we have the normal force, and we also have the y component of the applied force, 22.5. In the downward direction, we only have the force of gravity, 117.6 newtons. So this means that the normal force is going to be 95.1 newtons. The fact that we are pulling up on this box decreases the normal force. We are supporting some of the weight of the box, and then whatever we don't support is balanced out by the normal force. If we were pushing down at an angle, that would make things a little bit different. We would have two downward forces and one upward force. So now we can calculate the force of kinetic friction. Again, the force of kinetic friction will be the coefficient of kinetic friction times the normal force. So that's going to be 0.3, the coefficient of kinetic friction that's given in the problem statement, times the normal force of 95.1 newtons. And that gives a force of friction of 28.53 newtons. Now we're ready to solve for the acceleration of the box. The net force is the individual forces added together. And so we have, looking at this, we have two forces that are acting horizontally. We have this applied force, the horizontal component of the applied force that's acting to the right, and we have this force of friction that's acting to the left. Again, as I set this up, I'm going to choose the right to be my positive x direction. So my net force is going to be 38.97 newtons plus the force of friction. But since the force of friction is acting to the left, that's going to be negative 28.53 newtons. And so together, we can see that the net force is going to be 10.44 newtons. Besides the individual forces added together, the net force is also equal to the mass of the object times the acceleration of the object, which is going to be 12 kilograms times the unknown acceleration. And so by putting those two pieces together, we have that 10.44 newtons equals 12 kilograms times the acceleration, or we get an acceleration of 0.87 meters per second squared. So this problem is not much more difficult than the other problems, but one of the key things is recognizing that because this applied force is acting at an angle, we need to break it into components, and that means that the normal force is not just going to balance out the weight. When we go through and look at this, a common mistake that students will make is to always set the normal force equal to the weight of the object. You have to make sure that all of the forces perpendicular to the ground add up to equal 0. If there's only the normal force and the weight, if those are the only two forces perpendicular to the ground, then the normal force will balance out the weight. But a lot of times you will have more than those two forces acting in that perpendicular direction. And so you need to make sure that they're going to balance each other out. Or sometimes the full weight won't be acting perpendicular to the ground, as when we have an object that's on an incline. Again, you need to look at that perpendicular direction and make sure that those forces balance out. Once you do that, then it's going through finding the forces, finding the net force, using the net force to get the acceleration, just like any other force problems that we have been doing. In this problem, we have a car with a mass of 2,500 kilograms, and it's traveling at a constant speed of 14 meters per second along the road. The driver sees a traffic light turn red, and he slams on his brakes. His wheels lock, and he skids to a stop in a horizontal distance of 25 meters. And what we're going to do is we're going to calculate what the coefficient of kinetic friction is between the tires and the road. So looking at this, there are three forces that are acting on the car. One force that's acting on the car is the downward force of gravity. So it's 2,500 kilograms times 9.8 meters per second squared. So we multiply those together, we get 24,500 newtons. The force of friction acts parallel to the surface, and because this car is skidding to the right, the force of kinetic friction is acting against the direction it's sliding, so the force of kinetic friction acts to the left. There are no other forces acting perpendicular to the ground other than the normal force. So in this case, the normal force is going to be 24,500 newtons also. It's going to balance out the weight. Those are the only three forces that are acting on the car. A mistake that some people make is that there must be something pulling the car forward. There's not. There's no forward force that's acting on the car when he's applied the brakes. When he hits the brakes and the wheels lock, there's nothing pulling on the car forward. The car is moving forward, but there's a difference between forward motion and a force acting the forward direction. The only force that's acting on this car is the force of friction, causing the car to slow down. If the wheels were still rolling, there would be friction between those tires and the road that would actually be pulling the car forward. That would be something different. But in this, the wheels locked, and the friction is acting against the motion of the car and causing it to stop. Now, to solve this problem, you have to recognize that the first thing that you need to do is calculate the acceleration. So we're going to need that acceleration to get the net force that acted on the car. So we know that the car started at a position of 0 meters and it ended at a position of 25 meters. Again, if we can choose the origin to be wherever we want. So since we know that it traveled 25 meters from its starting point, the easiest thing to do is to set the origin to where the car starts. We know that the car starts with a velocity of 14 meters per second. Again, the way that I've set this up, saying that the velocity is positive and also saying that the final position is 25 meters bigger than the starting position, I'm setting this up so that the right is the positive x direction. The car eventually stops, so the final velocity is 0. So we're going to need the acceleration. And something that sometimes we're given in the problems, but not in this case, is time. And so to go through and solve for the acceleration, we're going to look for a way to do it that doesn't involve the time. And that would be to use the equation that relates the velocity and the position. The final velocity squared equals the initial velocity squared plus 2 times the acceleration times the displacement, x minus x0. And so plugging in those quantities, we have that 0 squared equals 14 squared plus 2 times the unknown acceleration times 25 minus 0. And solving that out, we get that the acceleration is negative 3.92 meters per second squared. And here, this negative sign means that the acceleration is in the opposite direction of the velocity, which means that that acceleration is going to be acting to the left. So then, once we know the acceleration, we can find the net force. The net force acting on the car is the mass of the car, 2,500 kilograms, times the acceleration of negative 3.92 meters per second squared. So this gives that the net force is negative 9,800 newtons. Looking at the diagram, we can see that the net force that is acting on the car is this force of friction. And so because we're setting this up so that the right is the positive x direction, and because Fk is referring to the size of the force of friction, we have that the net force acting on the car is the opposite of the force of friction. It's the force of friction acting to the left. It's negative F sub k. Again, one of the ways to look at this is we can think of the force to the right, which is 0, plus the force that's acting to the left, and we make that force to the left negative. And so when we put those two things together, we get that the net force is negative F sub k. And so from this, we have that negative F sub k equals negative 9,800 newtons, or that the force of friction was 9,800 newtons. Again, remember, F sub k is standing for the magnitude of the force of friction. And so then using the equation for the force of kinetic friction, we have that the force of kinetic friction equals the coefficient of kinetic friction times the normal force. So we would have 9,800 newtons equals the coefficient of kinetic friction times the normal force, which was 24,500 newtons. And this gives us that the coefficient of kinetic friction is 0.4. Again, the coefficient of kinetic friction is a unitless quantity. Now, in this problem, we were given what the mass of the car was. One of the things that you should recognize is that this problem would have worked out exactly the same for any mass of the car. If it stopped in a distance of 25 meters, that coefficient of friction was 0.4, no matter what the mass was. And the reason for that is because The normal force would have depended on the mass, and the force of friction, which was the net force, has the mass in it, and so the mass would have divided out. We would have had the mass times negative 3.92 as the net force, and so this would have given us that the force of kinetic friction was positive m times 3.92, and we would have set m times 3.92 equal to the coefficient of kinetic friction times the normal force, which would have been m times 9.8. And you can see right here that the mass would have divided out. The coefficient of kinetic friction was just 3.92 divided by 9.8. Again, this is important to recognize because sometimes when the mass of the car is not needed in a problem, they won't give you the mass. And so one of the ways of doing that is to use a variable m for the mass, and you can see that it divides out. Another way, it's probably not quite as mathematically correct, would be to make up a mass for the car. And again, you could see that the mass of the car would divide out. The more proper way would be to use a variable m for it so that you could see for sure that it does divide out. But for some students, it is easier to just put in a mass for the car.